Let us consider that we have two conductors. I'm drawing arbitrarily shaped. Let's call this conductor 1 and conductor 2. And what I do to this conductor, to this geometry of these two conductors, is I connect a battery, and let's put a switch and a battery across these two places. The space between the conductor could be air, or what we call free space. Free space is where you cannot have any induced charges, or it could be a dielectric. Let's first turn this battery on. So the switch is turned on, and I have some potential difference on the battery V naught. What would the battery do? The battery would start stealing some charge from the bottom conductor, lift this charge up, and then start depositing it on the top conductor. And this will keep on going on till you get charge Q, which would be the capacitance of the system multiplied by V naught. So till this condition is met, till the potential difference across the two conductors becomes equal to V naught, a battery will steal some charge from conductor 2 and deposit it on conductor 1. So I would end up getting some positive charges on conductor 1, and since the charge has been stolen from conductor 2, I would get negative charges on conductor 2. And there would be an electric field which would be created between these two conductors, and the potential difference between these conductors, when I go from 2 to 1, let's say we just walk across this path, that potential difference would become equal to V naught. This arrangement of two conductors separated in space is a very important arrangement. And this arrangement is called a capacitor. So capacitor consists of two conductors separated in space by some dielectric. The dielectric could be air too. Doesn't need to be another insulator material, but for most practical purposes, we may have some dielectric in there. This plays a very, very important role. And what would this capacitance be? The capacitance of the system would be Q by delta V 2 to 1. Why does this play a role? Let's just think about it for a second. We had connected this battery and we had put some charge plus Q here, and similarly charge minus Q on the other conductor. The battery basically stole plus Q charge from conductor 2 and gave it to conductor 1. But once the charge has happened, there is electric field between these two charges. These two charges are attracted to each other. They want to go and meet with each other. They can't go through the battery, but they want to go and meet with each other. So they are attracted towards each other. Now, what happens if I remove this battery? When I remove that battery, this attraction has not gone anywhere. This attraction is still there. This charge Q, which is present on the two conductors in magnitude, one has plus Q, the other is a minus Q. That charge Q is trapped there. And there are forces happening between these two charges. This charge is being attracted towards each other. So there are forces happening between these charges, and whenever you have forces, that means there is energy stored here. And this energy is being stored in electric fields. So this is a device. So effectively, if you think now, capacitance is a device which allows us to store energy in electric fields. You will analyze this capacitor as you put in circuits, and you will see there that this energy is available for you to give when you want to give it. I can go, if I want to extract that energy, I can go and do that. So you will see in ECE 140 how this stored energy affects the circuit performance. You can store energy and then you can give it to a circuit when you want to do it. So thus capacitors are play a very important role in our field. They're used in electronic circuits quite a lot for applications like smoothing, for filtering, bypassing, and even resonators. You should see some of these applications. You should definitely see filtering and smoothing in ECE 140. And in ECE 240, you would definitely see smoothing and bypassing applications of a capacitor. Capacitors also play an important role in many sensing devices. The screen I am writing on, this touch screen, is a capacitive device. As I bring my finger closer to the screen, I bring a material of different epsilon, different dielectric permittivity, and we will see soon that the capacitance would not only depend upon the geometry of the conductors, it also depends upon the dielectric permittivity of the material surrounding the conductors. So when I bring my finger close to the capacitive screen, the dielectric permittivity changes and the capacitance around that point changes. And an electronic circuit picks up that change of capacitance to decide where I touched and what I wanted to do on the touch screen. There are many other places where you can see capacitors, accelerometers, for example. The accelerometers you have in your smartphones are effectively, not as simple as I would draw, but are effectively a capacitor where one plate is allowed to move with some spring on it. As this plate moves, the capacitance changes, and the speed with which, or the frequency with which this change would happen, would be related to the acceleration. The seatbelt tensioners in your cars are also effectively capacitors, and both these applications are built based on what are known as micro electromechanical systems. So these are mechanically moving parts normally made on silicon, about few tens of microns to 100 micron in size. Just to put this distance in perspective, a typical human hair is about 30 micron in size. So you can see that the capacitors play a very, very important role in our field. And your project is going to is for you to think of using capacitor in some sensing application. What we are interested in doing, and in EC 106, what we would be doing is trying to understand what capacitance is. How can we have some conductor geometry with some material in middle having epsilon, dielectric permittivity epsilon. How can we go and calculate capacitance for it? Any arbitrary geometry consisting of two conductors and dielectric in the middle, how can we calculate the capacitance for that geometry? That's what the goal for this chapter is. That is what we would focus on in ECE 106. In ECE 140, almost at the parallel time, you will see how you can take this circuit element, put it in a circuit, and how it would respond to a circuit. First, starting with DC sources, and then going to transients. You just turn a switch on. What would happen when you have a capacitor, and then with AC sources. That's what you would see in ECE 140. Let's describe some of the values of the capacitance. So what we are really interested in calculating is what would the relationship be between the charge, let's say this is conductor 2 and conductor 1, the potential difference which is created when I put this charge Q in. Few things to remember. First, capacitance is a property which depends on geometry. It doesn't depend on Q, or V. We are still working in the linear regime. It only and only depends upon the geometry of how the conductors are placed, and what material you put in the middle. Another thing to note is that capacitance exists even when the conductors have no charge. Please don't think that capacitance only happens when I put charge on the conductors. Capacitance exists even when there is no charge. When I put a charge on the conductor, then the potential difference which is created would be related to that capacitance. Or if I put a battery where the V dot would be equal to this, then the charge which would be deposited on the conductors would be given as CV dot. Just like me, my mass exists even if I go to a region where there is no gravity. My weight there would become zero, but my mass would still exist there. That mass is an inherent property belonging to me. How it manifests itself into a force depends upon what gravity I am in. The same way, capacitance exists whenever you have two conductors next to each other with some air or dielectric between them. What matters is what matters what would then happen is if I put some charge or if I create some potential difference, then the charge and the potential difference would be related to that inherent property, the capacitance. So please keep this in mind. Another important thing, at least in what we are doing, capacitance would be always positive. Capacitance, as what we are going to be calculating, would be always and always positive. What does that physically mean? It means this: Q is CV. It means that if I increase the value of Q, I make this Q, then my potential increases too. So when charge increases, potential increases. That's what the positive value of capacitance is. Now, in recent years, starting about 10, 12 years ago, there has been, in research, there have been cases of negative capacitance. The first time I think this was discovered was around 2009 in ferroelectric materials, and my group was the first one to discover it in semiconductors with a light interaction. Negative capacitance means that when charge increases, potential decreases. There are some of research topics right now where this negative capacitance has been observed. But everything we are doing in this course would be positive capacitance. So if you get a value of negative, there is some error you have made. Please keep this in mind. Three things you should keep in mind. Capacitance would only depend upon the geometrical properties of the conductors and the dielectric material in middle. Capacitance exists even when you have not put any charge on the conductors. And as we will discuss it, capacitance would always be positive. Alright, next we will see how we can calculate capacitance for any arbitrary shapes.